Cool. Welcome everybody to our talk. It's called A Process is No One, Hunting for Token Manipulation. A little nod to the House of Black and White from Game of Thrones if you're a fan. There's no spoilers. Well, there actually may be spoilers, I guess, but if you haven't watched that season yet, then,
It's on you.
Yep. So I'm Jared Atkinson. I'm the Adversary Detection Technical Lead at Spectre Ops. I do a lot of development, probably most notably for Power Forensics, which is a forensics-based toolkit for PowerShell. Contribute to things like OS Query. Previously, I worked in the U.S. Air Force. That's kind of where I got my start on their hunt team, and then worked for Various Group's Adaptive Threat Division after that.
Yeah, I'm Robby Winchester. I am the Adversary Detection Lead at Spectre Ops. Worked with Jared for quite a while. Co-author of ACE with him, and have also worked on Helk. I used to be in the Air Force as well. I was mainly on the other side doing red team, physical security and penetration testing and all that stuff, and then came over and started hunting. And I was also at Various Group's Adaptive Threat Division as well. So we're going to start on our quest, just like Aria starting at the beginning. So what are we here to talk about? So the first thing, a little bit of background. So hypothesis-driven hunting. There's a lot of people who talk about hunting. And it means a lot of different things to a lot of different people. Our kind of perspective and what we feel like hunting should be is ideally you come up with a hypothesis and you search for that in your environment. It's ideally going to be some type of targeted activity, and you're looking for things that have evaded your in-place defense. So the benefit of having a hypothesis rather than looking for bad is it's going to focus your data collection effort. We've had a lot of, we're consultants, so we go to client sites. We've had a lot of clients who go and they're like, we open up Splunk and we have 1 billion events. What do we do? And if you look at that as a whole aggregate of 1 billion events, then yes, it's a huge problem to solve. If you break that down into you're looking for a specific thing and you have a specific purpose and you understand what should be there and what shouldn't, it's going to make it it's going to make that 1 million events maybe 100. And 100 is a lot easier to solve than 1 million. And that's that analysis paralysis that you often see. So what are we looking for when you're building a hypothesis? So has everyone seen the pyramid of pain? So most of the security toolings that are in place that you have in an environment like antivirus, proxies, et cetera, they're typically going to be functioning kind of at that lower level. So they're going to be taking care of the hash values, looking at tools that are known bad hashes, IP addresses of things that have done malicious things in the past, domain names. As you go up, it gets a little bit harder to detect, but it's also harder to change. So how difficult is it for someone to recompile a binary with a different hash? Pretty easy. How difficult is it for someone to change the actual mechanism in which Mimikatz is able to obtain credentials from LSAS? That's pretty tough because that's kind of fundamental to it. So I can write my own Mimikatz, that's easy, but the actual TTP, that technique, that's where we want to be focusing. So I say techniques. What are they? We're former military. For us, TTPs, it means a very specific thing. So throughout the course of this, or anytime, hopefully you hear anyone from Spectre Ops talking, they should use it this way. So tactics, techniques, and procedures, they mean specific things. So this is out of DoD, like joint publication, applied to cyber as well. So a tactic is the highest level. That's the big group. So that's the employment and ordered arrangement of forces relative in relation to each other. So like to use an analogy of car ownership, you want to take care of your car. A tactic of car ownership would be preventative maintenance. It's a huge category. It covers a lot of stuff, but it's kind of like one specific focus. Then you have techniques, and that's the non-prescriptive methods or ways to perform a mission or task. So in the case of preventative maintenance, that would be changing your oil. It's a specific task that has other things underneath it, but it's like one specific area. There's also other things that you would do that would be underneath that preventative maintenance tactic, but that's the technique. And then finally you have the procedures. And procedures is where a lot of times we see people like targeting. That's those hashes and IP addresses. So that's the very specific, standard, detailed steps on how to do it. So like, this is the oil that you should use. This is the filter you should use. This is how often. So as you go down, you get more specific, but it's also going to be more varied. And so that's where, when you're building these hunt hypotheses, ideally you want to focus at that technique level. And that's what we're going to talk about with our case study. So how does this apply? Has everyone in here heard of MITRE ATT&CK? Hopefully. Okay, awesome. So to kind of break it down, MITRE ATT&CK is built out as tactics, techniques, and procedures already, if you did not know that. So the tactics, essentially, are that top column. Each of those categories is a tactic that can be used. Each of the actual entries is a technique that would be implemented. So as you're building hypotheses, the techniques are where you're going to be wanting to focus. And then finally, when you actually kind of click and zoom in, you'll get to the procedures, which is that detail. It's going to say, APT 29 did this with this tool, this command was run, these accounts were added, like all of those types of things. It's that tactic, technique, and procedures breakdown. So we want to focus on that technique. Now that we've got the background, let's talk through our hunt hypothesis that we were going to go through here. So what's our process? We talked about this in a lot of depth last year at our DerbyCon talk, but we're just going to cover it now and then go through a practical implementation of that. So we found it's really hard a lot of times to actually create a hypothesis. People say hypothesis-driven hunting, but then what do you make a hypothesis of, and how are you consistent, and how do you track that? So we kind of break it down into these 5 steps. So identify the tactic and technique you want to focus on, identify the procedures, identify what the collection requirements are in order to detect that behavior, and then identify the scope, and finally identify the excluded factors, which is what stuff did you knowingly ignore because you're trying to solve a problem. So the goal here is you make a hypothesis targeted for a 1-week execution window, and you solve that small problem, and it's your environment, you're there, so iteratively over time, you're going to slowly knock out some of those techniques, and that's going to allow your environment to get more robust. On the alternative, if you just try and solve random problems, like you don't have an approach, you're kind of letting the adversary dictate what you're doing, and you're going from threat report to threat report. So now we're going to actually get into the meat of it. So this is our case study of detecting access token manipulation. The scenario situation that I'm sure no one can relate to, you have a small security budget, you don't have any EDR because that costs money, you have basically no lateral network visibility, and people have to install their own printers, so everyone's a local admin, because why not? So your CSO went to DEF CON and saw this building an empire with PowerShell talk, and they come home and they say, can we detect PowerShell? Can we detect PowerShell Empire? Like, we want to detect this. So our task is, can we detect it? Can we stop it? Have we been affected by it? But really, when we get down to it, we're not wanting to just detect PowerShell Empire, right? We're wanting to detect that entire family of things. So if someone goes and makes a new tool set, our detections are able to translate across multiple different tools. So high level, again, the first step, tactic and technique. What are we going to look for? Empire uses a ton of tactics and techniques. It's a full-featured remote access tool. So in this situation, rather than trying to focus on everything and probably getting nothing, we're going to focus on one specific thing. So Empire is used for all of these different things: privilege escalation, defense evasion, credential access, lateral movement. We happen to be doing some research into the privilege escalation, access token manipulation. So that's the only thing we're going to focus on here, is the tactic of privilege escalation and the technique of access token manipulation. That's not to say that there's not valuable other hunts to happen, but this is what we're going to focus on so that we can solve this problem. We'll deal with all that other stuff at another time. Who has run Git system in Metasploit? Anyone? Okay, so that's actually access token manipulation. That's going to be that token impersonation where you're impersonating the system token, doing token theft. So that's what we're looking for. That's built into tons of security tools. So what are the procedures? This is those specific examples, right? We talked about how it's used. So this is where we're going to want to go and do the research, go and find what are the different mechanisms, how are access tokens being manipulated by different tools. To kind of understand that, we have to go through and understand Windows authentication. So when you log in, there's more than just you put in credentials and then something happens and you get an access token. So essentially the process is, once you log in, you provide your credentials, and then Windows is going to create a logon session once you've completed that authentication. And then the credentials can be reused later, like that can be NTLM hash, Kerberos tickets, passwords, whatever, but it's going to create a logon session. Now that logon session is going to be what's going to allow for you to not have to put in your password every single time. Access tokens are the kernel objects that are associated with process and threads that are derived from your logon session. So that's going to let a process or thread know what level it needs to execute at. For logon session types, there's really two that matter, not network and non-network. So the network logon types like WMI and WinRM, if you've heard talk about like exposing credentials, they do not load your credentials into LSASS. Shit, they're all in. I talk with my hands a lot. I have to like hold them. They're in memory, or they're not in memory, so you don't have to worry about exposing them. Whereas the non-network, like console, RDP, when you actually interactive log on, those are going to expose your credentials. So we're not worried about those type 3 logons, those network logons. And then finally, the token types and impersonation levels. So there's 2 general types of tokens. There's a process token, the primary token, which is a process token, and then there's impersonation tokens, which is a thread token, essentially. Each thread can have an impersonation token. Now, it might use the primary token, but it also could potentially use an impersonation token, and there are legitimate reasons for that, which Jared's going to get into in a little bit. So I'll hand it over to Jared.
Yep. Okay, so to kind of recap the little research piece that Robby discussed, every process has a primary token, right? Threads can have their own token called an impersonation token, but by default, they will inherit the primary token from the process, right? Attackers, of course, can manipulate the tokens, apply different tokens to the thread that they're executing from, and then they're able to operate kind of under the context of a different user, or maybe a more privileged user. Kind of going through and talking with maybe some red teamers, some of our offensive research guys, we've kind of broken this up into 3 different kind of procedures that you might use to accomplish access token manipulation. One is token impersonation or token theft. Another one would be create a process with a token. And then third is make and impersonate token. And so I'll kind of talk about how those work, right? So token theft, this is that kind of get system attack where you directly steal a token from a running process, right? Your target user has a non-network logon session on the system. And so this could be like a process running a system, like WinLogon or something like that. Or it can be maybe a domain admin RDP'd into a system and you want to steal their token. And you call duplicate token EX, open process to the process that you're interested in, duplicate token, get a secondary token, and then you can apply that token to your thread using impersonate logged on user or set thread token. And so to kind of show how this works, we have PowerShell and we're wanting to impersonate WinLogon. We call open process, get a handle to WinLogon, and then we call duplicate token, so we get a duplicate system token, and then we can go ahead and apply that to our specific thread. So now any code that's running in that thread is going to operate as the system user, right? So that's kind of how that's working under the hood. The second is create a process with a token. So for one reason or another, the attacker wants to run a second process, right, outside of kind of the current context. But that second process, they want to run it as a different user than who they currently are operating as. And so similarly, they're going to call open process, duplicate token, get a copy of that token, but then they could call create process with token W, or create process with token. And so this kind of looks like this. So Explorer, we have domain admin logged in. We can open process, then we can call duplicate token, and that will get us a duplicate domain admin token. And then we could call create process with token, and that's going to create malicious.exe running as domain admin. And I want you to notice that malicious.exe, the primary token is that domain admin token, right? So that's maybe an interesting differentiation when we're developing our hypothesis here. All right, so, and the third is make and impersonate token. So this is where you have a username and password for a user that you want to target, but maybe they're not logged into the system that you're on. And so you want to somehow impersonate them, but you can't just steal a token directly. And so you call logon user with a specific logon type called login32 logon new credential. And so this is a type 9. If anybody's ever used run as /net only, that's exactly what that's doing, right? And so attackers realize that they can do this, create a new logon session for the user that they want to impersonate using that username and password, and then they can call set thread token and apply it to themselves. And so that kind of looks like this. So I pass in the domain, username, password, type 9 logon, create a new logon session. Locally, I'll be running as my current user, John Doe, but on the network, I'll be running as this domain admin. And then I could call set thread token to apply that to my current thread, and now I'm operating again locally as John Doe, but on the network as domain admin. And so that's kind of interesting. One of the interesting things about that is when I query the primary token or that impersonation token, it's going to appear as if John Doe is the user that it's running as. But as we mentioned, on the network, it'll be running as domain admin. So we might want to think about how we might detect that type of relationship. All right, so we've kind of identified that we have 3 different procedures, but remember for create a process with token W or create process with a token, that's creating a primary token, right? So we're impersonating using a primary token, and so maybe that's a little bit different of how we might detect the activity, and so we're going to go ahead and drop that out for this hypothesis. Otherwise, we're going to have like scope creep and get a little bit out of control, and so we want to kind of narrow it in so we can actually focus on a problem. All right, so identify collection requirements. So this is kind of the third phase. The idea here would be to maybe find some proof of concepts for these attack techniques, kind of use them in a lab, and start getting an idea for how this might work and how you might detect it. What data do you need to collect, that kind of thing. So we might use real malware or proof of concept malware, open source things like Incognito and Metasploit. We can use, Empire has invoke token manipulation. There's tons of different options, but we kind of want to go through that process. And so here we go through and start interacting with different tools, collect relevant data points. Ultimately, we found that access tokens for every process and thread are very valuable for identifying this type of activity. And then we found out that Kerberos tickets for each logon session might be interesting, and I'll show why in a second. And so collecting access tokens, we end up writing a PowerShell script that's going to do this. You enumerate every process, you open every process, query its token, and then you enumerate every thread and then query its token. If the thread has an impersonation token, it will return. If not, it will say, hey, nothing here to find. Go ahead and reference the process token. And so ultimately we have get access token, and we have a bunch of information like what's the process name, who's the user for that token, what groups are they a part of, what privileges do they have, this is a primary token, all that kind of stuff. Here's what benign impersonation ends up looking like from the perspective of get token. Get access token. And so the process name here is SVC host, which SVC host, for those that know, is the service host process. Its whole purpose is to host other services, right? Other processes. And so the idea here is it's running as a normal user, but it's impersonating a normal user, this tester user here. But it's originally running as system, and so we go from system level user, and we're impersonating a lower, just normal local admin user. And so in that case, we have what I call like kind of downward impersonation, right? So you're impersonating a less privileged user, and in that case, we're not necessarily quite as worried about it. As opposed to kind of this impersonated system token, we have PowerShell, who's the primary user for the primary token is tester, right? A normal local admin. But the username that they're impersonating is system, right? So this is like an upward impersonation, and this might be something that we're interested in. And that's, in fact, PowerShell Empire doing impersonation. And then for ticket granting tickets, we're going to enumerate the logon sessions. Ticket granting tickets are associated with every logon session that's performing Kerberos authentication. And then we're going to go ahead and just query the ticket itself. And so we have get Kerberos ticket granting ticket, which gives us a bunch of information, such as what type of ticket it is. KRB TGT indicates that it's a ticket granting ticket. We see the client, local admin, and the domain. And then here's a benign ticket granting ticket. So again, we have a logon for local admin at Citadel, and we have a ticket for local admin at Citadel, which is kind of what you would expect. And then here's a situation where we have a negotiate logon session for a user John, local user, who's requesting MikeWright_A at Citadel, the ticket. And so generally you want to probably request a ticket for the user that the logon session belongs to. And if that's not the case, that might be something that indicates something strange is going on. All right, so we kind of have identified what we're looking for, how we might gather data to help us derive that hypothesis, but then we want to identify the scope, right? So how do we want to run this across the entire network? Is that feasible? Where do we have collection? All that kind of stuff. And so that's kind of what this identify scope phase is. And so we want to do this over 1 week. We have 3 domains with 1 Linux server, which doesn't have access tokens, 9 Windows workstations, 2 Windows servers, and no sensitive systems. So we're just going to hit basically all the Windows systems. And then we want to document excluded factors. So what did we expressly exclude throughout our hypothesis? And so, for instance, other privilege escalation techniques that maybe we want to circle back to later on, maybe credential access techniques like credential dumping, lateral movement. There's a couple situations where we're not able to elevate to system to actually gather the data that we need, and so that might be something that we want to circle back on it as well. So the point of this part of the process is to really identify what did we leave out and what do we need to do in the future or think about in the future to really answer the initial question. All right, so we have a demo. This is from a red team training class lab, so it's a little the network's a little dirtier than what a normal network would be, surprisingly. Yeah, hopefully. So I think I have it. Go tell it to play. All right, so generally speaking, I created a PowerShell remoting session so that I could run this PowerShell script across all these systems. There's 12 systems in total. Here I'm collecting tokens. One system returns saying, hey, you're not able to elevate to system. A kind of interesting trick to collecting tokens is that you have to impersonate system in order to collect tokens for all the processes. Similarly, I collected Kerberos tickets. And so we end up with, I'll show it here in a second, quite a number of tokens. And this is what a token looks like. So we have a process name that's associated with the process ID. We have the username for the token itself. And then we have information on the primary token, which in this case, it's a primary token itself, so it's going to match up. But in the case of impersonation tokens, that information will be different and allow us to really kind of identify what's going on. And so initially, we have 633 tokens, but we'll start kind of narrowing in on the tokens that actually matter to us, particularly impersonation tokens. And so here we're looking for tokens that aren't impersonation, or not primary. So we have 104 impersonation tokens. And then we're going to start narrowing in and say, hey, we want to look at impersonation tokens where they're not impersonating themselves, right? So any impersonation token where the primary username and the username are not the same, and we get down to 49. And so usually this is a lot smaller, but because this was a red team lab, there's some craziness going on, and so there's a lot of bad stuff. All right, so now I'm going to show kind of like the actual output, the process name, process ID, primary username and username, and then I think the computer name that it's on, and so we can throw that out. And so we start looking through this, right? And so first things first, I start identifying that, it looks fairly consistent. So on the right, you see the computer name, and you see that there's like one, it's all SVC host. You see that there's like one system impersonating a user, and then there's a bunch of network service impersonating a user. It's pretty consistent, but it's also all downward impersonation. So it ended up that there was no actual like system token theft in this lab at the time that we ran this. And so we're going to go ahead and look at tickets, right? So again, we have those tickets. We have 76 tickets total throughout the 12 systems. And we're going to start kind of narrowing in again where the session username is not equal to the client name, right? So I have a logon session for Jared. I'm probably going to request a Kerberos ticket for Jared. And in cases where that's not the case, I might be interested in investigating that. And so, again, I think we narrowed it down to like 26, but we can start looking at the actual information here. And so we see, for instance, a bunch of use cases. So we have like this John user again, who's impersonating a bunch of people. We have Andy Robbins, DA, impersonating Matt Nelson, DA, from a different domain. We have John impersonating Mike Wright _A. There's a bunch of crazy stuff going on. And so we're just going to pick out a couple things, but these John users ended up being, anybody familiar with PowerUp, the privilege escalation tool? So the default user that PowerUp will create is John, and so that's what that ended up being. And so we'll kind of go in and start investigating some of this activity, and one of the ways that I like to do it is you have a logon session ID associated with it, and you could use PowerShell to query the processes that are spawned within that logon session, and so you can start kind of identifying what's going on there. And so here I'm going to look for these Andy Robbins DA, the top ones. I'm going to start looking through them and seeing if any of them show any signs of like malicious or suspicious processes going on. The initial thing is we're saying, okay, well, it's weird for like one person to request a ticket for another person, but it's not necessarily bad, right? So there's tons of weird things, security products, all kinds of weird things that are doing stuff, and so we want to that gives us a point to start investigating, but it doesn't mean that we should immediately call it malicious. And so we start rolling through, and eventually we find that there's this PowerShell with an encoded command running within one of those logon sessions, and so I'll save you the effort. You could decode that base64 and it ends up being an Empire agent, right? So we were able to detect Empire without actually like directly trying to detect Empire, right? Through a more technique-driven kind of focus. All right, so that's the end of our time and that's the end of our presentation. We're happy to stay outside and chat with anybody that wants to talk, so thank you guys.